Can you hear me? Yes. Okay. So thanks, Binkai and Fanbu for the invitation. And it's always very nice to come to this department. I've been here, I was here 2019. And I think I always know a lot of friends here. And then every time I come here, and I was in the stat department in 2023. So every time I come here, my friend list like increased. And on my Chinese WeChat, you know, the friend's name, like the list just keep increasing. So I almost feel that the Michigan stat department and biostat department is almost like my kind of have this homecoming feel every time I come here. So it's really nice to come here again and present some work, actually recent work of mine I'm pretty excited about. Okay, so I'll get started. So I'm actually today going to talk about something really classic, but with a new actually angle to it. So it's a sample size and power calculation for causal inference, but the key thing is it is in observational study. Okay, so I will. This is a joint work with actually my student who's now my student who now work in industry, and this is all the heavy lifting he did, all the creative work he did. He's like the most creative student I ever had, and he's now in hedge fund earning millions. So causal inference, everyone knows causal inference. We want to evaluate effects of a treatment on outcomes. So of course, RCT clinical trial is the gold standard for causal inference, and we all know it's not always possible in practice. So more and more people do observational study. So we all know the central difference to observational study is confounding. Okay, so this is important. So of course, there's this concept called target trial emulation. This is a very fancy word that Jamie Robbins and Miguel Hernan, they come up with. Essentially, it's just say use causal inference method to mitigate the confounding issue and emulate a hypothetical RCT. And often people use propensity score methods. Okay, so regardless you're doing RCT or emulated trial, the first thing when you're at the design stage, unless you're doing those big population-based study, you don't need to worry about sample size. Unless in that case, but in almost every other case, actually the design stage, you need to do a careful sample size, a power calculation to know that how big your data would be. Again, people say that I do population study, then I don't need to worry. I have nothing to say with that. But in reality, is sometimes more and more people, like in rare disease, people go to actually recruit patients, and they want to know how many patients they need to have. Okay, so this is a classic problem. And again, I'm happy to it's fun to talk in a biostat department, because in a stat department, many people don't do this, but in biostat department, I'm pretty sure every of our faculty here probably at some point in their career asked to do a sample size calculation, power calculation. Okay, so I just quickly go through that. What is the power calculation, the definition, particularly in the treatment effect sense. So sample size calculation is to determine effect size of tau in a hypothetical hypothesis test, to determine the minimum sample size to achieve certain power 1 minus beta. Beta is the type 2 error, given a fixed level of type 1 error alpha. Okay, this is very standard statistical 101 problem. And of course, if you know the power, you know the sample size. So this is just reversed, right? So the typical input of a power calculation would look like this. The PI will tell you the effect sample size, effect size, say 1 or 2. And desired power usually 80%, type 1 error usually 0.05. And of course, because we're doing treatment effect, so you also need to know the ratio between the treatment group, the proportion of treated, say 50-50, then it's 0.5. Okay, so the key feature of power calculation is this is conduct before you have any data. You don't have any data. No individual data. At best, sometimes we're lucky enough, we have some summary information like covariates or outcomes of previous study, similar study. That's the best you probably have. And usually the effect size, the PI need to specify it for you. So this problem is actually well established in randomized trial. You can have closed form formula based on two sample z-tests. And I'm going to show you like why this is RCT is very easy. Okay, but it's much more difficult in trial emulation, in observational study. So what's the current practice? The current practice, the first is, well, to treat as if it's randomized. And everyone knows that's not a good idea because you often vastly underestimate the sample size. Okay, people know that's not. And the other approach is the variance inflation factor. But even this method, it's slightly more like with theory backed, but it still requires information often are not available. For example, one method asks you to give you the distribution of propensity score distribution, the weights. How do we know that, right? So that's, okay. So when I first come into this problem, because again, I got asked about this problem almost every month. Some collaborator asked me to solve this. And so I was like, well, this is simple. Like you probably all know, I make up some simulations to do that, right? So I'll just simulate data that match the pre-specified summaries and then calculate the power. Problem solved. I will generate individual data. But you probably all, if you have done this before, you probably all had the experience like, depends on what model, simulation model you choose, what parameters you choose, the result will be vastly different. So this is basically a massive fraud in terms of grant proposal writing. You come up with something and you tweak the model or tweak the parameter to say that this is the sample size I want, right? That's basically what we do. And so really it's, I mean, I say mathematically, the statistical challenges, it's actually not clear. What are the summary information? Summary statistics is really needed to uniquely identify under certain like, under like mild assumptions, can uniquely identify the data generating process. So existing method, again, this all ad hoc choices between possible data generating models. So we want to avoid that. So what I try to do in this study is I try to answer the question, what are the summary statistics are sufficient to uniquely identify data generating process in observational study that is not too many assumptions? The second is, of course, with those statistics, I want to come up with a formula for the analytical formula for you to do things, okay? So it's a very fun, turned out to be a very fun journey. I'm not sure whether I have enough time to talk about all the details, but I can give you our answer, like, I show you what we have done, what we have found. We found that actually, we find that to determine the minimum sample size or do the power calculation of observational study, first of all, you would need those standard inputs in the power calculation for RCT, like what I just put, the alpha, beta, tau, and the treatment proportion. But on top of that, you actually don't need too much. You only need 2 more parameters. That's enough. And these 2 more parameters, I actually hit. So what are the 2 parameters? One, actually quantify. Okay, so again, if you have done causal inference, you know, when we say confounder, we call it X, this is a treatment, this is outcome. A confounder has to, what is a confounder? Confounder essentially is a variable that is correlated with the treatment, also with the outcome. So essentially, the confounder has 2 paths to affect in the whole data generating process. One is this. So this is basically the confounder treatment, this path. This is a confounder outcome path. So essentially, you only need 2 parameters. One parameter, this I call the overlap coefficient, which I'm going to define, is to quantify the strength of this, the correlation between these 2. And the other is a confounder outcome association. It's actually turned out to be, we can use R squared to approximate that and to quantify this strength. And this makes perfect sense because we know the difference between RCT and observational study is the presence of confounders. And what is confounding? Confounding is a variable that is affect both treatment and the outcome. So there are only 2 paths. And indeed, under some mathematical formulation, indeed, when you do trial emulation, you need those RCT inputs. But the extra input is actually not too much. You need 1 to quantify this arm, 1 to quantify this path. So then we provide theoretical. So how do I get that? That's the next 40 minutes. I will give you the story. provides theoretical justified, and I say something ning. This is common language in causal inference. Analytical formulas. So again, any questions can just stop me at any time. Need some stat formulation because first notation, I just say we have a sample of n units. Of course, I need to find n, right? We use z as a treatment, x as covariates, and in causal inference, you have potential outcomes. Again, in RCT, there's no difference. The potential outcomes and the observed outcomes, they are kind of equivalent. But in observational study, there's a big difference, okay? So this potential outcomes, of course, the observed outcome is just one of the potential outcomes that is corresponding to the treatment that you observe. So for target estimate, the treatment, we will do this old, like average treatment effect. Of course, now people do HTE and stuff, but let's focus on the simple one. The average treatment effect, basically assume hypothetical everyone being treated versus everyone being control, then what the difference would be, right? Then we need to introduce propensity score because that is the key tool here. So propensity score is just a probability of X receiving treatment given the covariates. And that's important for observational study. Okay, so if you think of some power calculation, what you do is you need to start with an estimator. You have an estimand, you need to estimate it. And then your hypothesis testing will be based on that estimator, right? So what estimator do I use? You also need assumptions. You also, again, this is all standard. I have to assume that unconfoundedness, the overlap and stuff. So with this, this is basically my estimator. It's the hierarchy IPW estimator. Again, you can ask me, why don't you do outcome regression? Then you don't get this nice insight because it's far more complicated. Anyway, I know this is hierarchy estimator. It's basically IPW estimator. It's normalized IPW estimator. This will be my estimator. So this is almost like like doing a statistic class. I would say that, well, the next time how I do power calculation, I need to study the variance of this guy, because hypothesis testing is you need to have the variance of this guy. So this is my estimator of that estimand. Okay, everything starts on this. So let's denote the variance of the IPW estimator, the hierarchy estimator. So this is all standard. Okay, this is all standard. Let's consider a one-sided hypothesis test based on this estimator. It is just one-sided and stuff. So this is all standard, right? So we can, like, if we know the variance of the IPW estimator, if we know that, this is all standard. One-sided test, it's like this is a minimum sample size. Z is just a Z statistic, This is simple. This is all standard. This is basically the RCT, actually. This is RCT, actually, we still need to know the V. Right, the key thing is, if you know the variance of the hierarchy estimator, you can just plug into this, because tau is known, it's prefixed. Alpha and beta prefixed. This is all just quantiles. And so then the question becomes, analyze V. But more importantly, in power calculation, you don't have individual data. You cannot estimate this guy from a data. What you have is probably just, we try to approximate V as a function of a few summary quantities that are available at design stage. So the question is really hard. First of all, I don't even know what summary quantities I need to uniquely identify that. Even if I know, I need to come up with a formula to say that this V can be well approximated. So it's in a sense, it's a reverse problem. But that's clear, right? I set the stage. And so, again, this is also pretty, this is known result. We know that the hierarchy estimate is consistent as asymptotic and normal. So we basically have a form of what hierarchy estimator look like. So let's look at this. So this is basically the variance, right? We need to focus on this guy. Let's just look at one arm. So first of all, you look at this. This is really involves those potential outcomes. It's not the observed outcomes that add the first complication. So now let's think why RCT is easy. In RCT, propensity score is no. 0.5, flip a coin. 0.5, right? So then this is 0.5. And this also in propensity, that is the potential outcome. The expectation equals the observed outcome in that corresponding arm. So then this whole thing just reduced into this guy. This variance formula reduced into this guy. What is this? This is just as what, like this is like you can just have the variance. You have the standard error there. So minimum standard would look like this. And again, what is this guy? This is what we called this, like this is basically the effect size, the tau standardized treatment effect. That's the effect size, right? So this is, you ask your PI to specify that, and this is known. So that's why it's so easy. And actually, I forgot to put the R here because I hear at 7.5, but you can make it more complicated with R, but that's less of a concern, right? So what is this? This is exactly a two-sample z-test. That's why RCT is so easy. But observational study, way more difficult, okay? So let's look at the observational study. What are the challenges and how we tackle them? So we look at let's just look at this part, right? In observational study, this is much more complicated because, first of all, propensity score, you don't know. And even worse, in power calculation, you don't even have data to estimate those E. This is just something unknown. We don't know the distribution. And also confounding makes that this potential outcome distribution is different from the observed outcome distribution. So you cannot just like previously, you can just put, you can go to each arm. And even worse, that there's a numerator, denominator, they might be correlated. So then if you look at the expectation, you cannot just move the expectation to the up to the denominator and numerator. You cannot do that. So again, all of this is not a problem if you have individual data, you just estimate them. In design stage, we don't have individual data actually to do any of this. So then how? Okay, so then doing any statistical problem, I think the idea is divide and conquer. So let's have a closer look at see how can we decompose into something we can solve. So I rewrite this. This is basically, well, okay, this is something I can look more clear to me. So what I need obviously I need propensity. If I know the distribution of propensity score, this is a problem like this is, so there's three components here I don't know. One is the distribution of propensity score. One is the distribution of the counterfactual outcome, the potential outcome. The other is their correlation. Okay, so the first one, so this is basically what we need. If we somehow know this as a function of a few summary statistics, problem solved. But let's see what we really have. We don't have the propensity score. What we do have, we know the marginal treatment proportion. How many, like 50% or 80% are treated. So if you mathematically write it out, it's just the marginal treatment proportion. But I don't know the conditional version of that. I don't know, but I have something. I don't know this. What I might know from the previous study, I might know is basically the distribution of the outcome in each treatment arm. It turned out that we actually need to know too much of that. But again, this is what we need to know. And the covariance, you really don't know because there's no observational study, no really observed information about this. But you can see, this is a problem. How I think of it, this is really an inverse problem. This is maximum information I might know. This is information I need to know to do a proper power calculation, not this kind of whatever ad hoc simulation. And so what we need to do is we need to use the limited previous information on this side to recover the full distribution on this side under some reasonable assumptions. Okay, so how I do that? I'm gonna do one by one. So there are three components. I'm gonna attack that one by one. So I think the most fun part is the first part, the propensity score. Actually, I use that. But okay, so the first idea is, the first thing is, remember previously when we do this problem, we always say that let's gonna simulate some data, right? Let's gonna simulate some data. But immediately the question become, in reality, you don't have one-dimensional X. You have a lot of X. it's very difficult to simulate a high dimensional X and say this is your reality, right? So, but if we look at the no matter whether we have outcome model or propensity score is a binary. We usually use a logistic model to estimate that. Regardless, what we do is the common models for propensity score outcomes, we probably use a GOM. You can say you use machine learning stuff, but let's first do a simple thing, right? So you use a GOM. This essentially is a linear combination of the covariates X beta. It's a basic function, whether it's an outcome model or propensity score model, is basically linear. It's a GOM as a function of X beta. So the challenge is X is multidimensional. In reality, it's impractical to simulate one by one, because how do you know what your new study before you even collect the data, what that does that? So again, this is my student is just so creative. He was saying that, look, I'm not gonna simulate the X. How about we study the distribution of X beta? Because if I study that, then I can look at the propensity score. If this is a normal distribution, then propensity score, if the logit model is a logit normal, I know it's a distribution, right? And so he just, again, it's just so creative. He told me that, well, I think this should be a normal distribution. And then he actually proved that. And then we really find there's a one type of central limit theorem called Lyapunov Central Limit Theorem. Essentially just study the x1 to x, like a bunch of random variables, but they're independent, but they're not necessarily identical. Because I mean, covariates can be all sorts of different looks, right? With the mean and variance 1, under pretty mild regularity conditions, indeed, this goes to the X beta actually goes to goes to a single Gaussian variable. And then, I mean, that's again, the Lyapunov Central Limit Theorem, you can say, oh, the regularity conditions are really strong. And then I say, okay, this is great. So what I ask him to do is I say, take a bunch, I played with a bunch of, like I have a few data set I often play with. And some of them have 50 variables, some of them have 10 variables, some have 8 or whatever. I say that you run an outcome model or logistic model, and then I want to see their X beta, really their distribution. Look, they are all normal. Oh, you will say, how about this one? Well, precisely this Lalande data is a mixture data. It's a mixture of two populations. This further tell you that indeed, even you don't need, at best here, I only have like 8 variables, because this central limit theorem, of course, n need to be a little bit big, like p need to be big, but IHC is a benchmark called inference study. It's have like 50 variables and stuff. So you can see they are more or less quite normal. Again, sample size calculation, just think it's not an exact science. So we have to do some approximation, right? So you can see that here it's normal. So this is great.
I have a question.
Yeah.
Previous slides. You talk about the symptotic normality. Is the p goes to infinity?
Yeah, p need
number of
yeah, p goes to yeah, but that's the thing. And then I find that in reality, those are the study I do. Some of p are pretty small, like 10. They're still pretty normal. So that's like the kind of this Lyapunov give me the like kind of the theoretical basis inspiration, but it's also supported by a lot of empirical evidence. It's like we find most of even the p is like 10 is still good enough. So it's like, again, of course you can always construct the counterexamples, but all the data I've been working with, it seems to be good enough. And I think for power calculation, that's probably a good starting point.
I'm not changing the result. I just want to clarify it.
Yeah. No. I'm just saying that I was also to myself, this is too good to be true. So I actually look at that. Okay, so now with this kind of trick, things become interesting. Like I can do a lot of fun things. So first is distribution of propensity score. Remember, I need to do that. So in reality, so again, so Lyapunov, we want to use a single Gaussian variable to substitute X beta. And then I actually looked through the power calculation literature. I feel a lot of people indeed simulate just with a single variable, Gaussian variable. And now I kind of have theoretical footing for that. But then normally, how do we estimate propensity score in practice? We do a logistic model, right? So if I have so we basically say logistic model, and then if this X beta is a single normal distribution, then this basically say the propensity score would approximately follow a logit normal distribution. Okay, that makes my life way easier because a large normal distribution you need to characterize that. I only need two parameters, mu and sigma square. So that I know that I can actually get this propensity score. I only need two parameters. Okay, so if you want to identify two parameters, you need two constraints, right? So the first constraint is already there for you because we know the overall treatment proportion, essentially that's the expectation of the propensity score. Average overall X would be your treatment proportion R, which you will specify like 0.5. And so, but you need another constraint. So this is, again, intuition tell me probably you need something to quantify how the two groups differ, the overlap in terms of the covariates. Because again, if we work on causal inference, we know the overlap between two groups is the most important thing, right? So my intuition is like, yeah, you need to have measured the similarity between the X in the treatment group and in the control group. Then the question is, there's so many ways of characterize that. What's the way? Probably, how do we characterize that, right? So there's several considerations going into there. One is I want to have this, I can call this phi. I don't know how to do this yet, but I want to have a measure so that between, like I have R and phi, people can specify. There need to be a one-to-one map between these two. This is not automatic. Okay, I need to give a one-to-one map so this can uniquely identify the data, the one. And the other one is need to be easy compute because PI come to you, they might give you a R, they might give you a phi, and you need to go that to resolve my mu and sigma. If it's hard to compute, then it's a problem, right? You need to identify to how to compute. Then how do you do? Again, this student is just a genius, really a genius. He told me that, he said that, well, look, large and normal is something difficult to deal with. Why? Because large and normal, there's not even a closed form mean. It's hard to compute, right? So if you look at this, I have large and normal, but I would not even be able to write this R as a function of mu and sigma squared because there's no closed form. Then his idea is, well, he say that normal propensity score is between 0 and 1. So what are some distributions that used to actually on the range of 0, 1, and with a pretty nice, beautiful mass beta distribution? Okay, so he say, okay, how about we use beta distribution? I didn't actually have I'll show you. So it turned out that actually there's another paper, old paper, show you actually beta distribution does a great job to approximate large and normal. And you can see that really for every possible like large normal distribution, beta, actually you can find a beta to do this pretty well. And nicely is there's a closed form of this approximation. So, and another beauty of beta distribution is if now we approximate a large normal distribution by a beta distribution, I call AB, normally call alpha beta, but here alpha beta already used for type 1, type 2 error, so use AB. The nice thing is with beta distribution, you know the mean of a beta distribution AB. That is A divided by A plus B. Now, this is nice, right? Because I know this, my treatment proportion is the average, is the mean of the propensity score. If my propensity score is a normal distribution, it's a beta distribution AB, this first constraint is closed form. Nice. I just need a second one. A second one, and also you can prove, like again, this is an old paper. You can prove that this once you have AB, actually mu and sigma is closed form. If you solve A and B, again, I haven't solved A and B because I need another constraint. But if you have that, mu and sigma squared closed form, you can just solve it. Okay. And of course, I need a second constraint, the overlap coefficient. Again, this student is a genius because I had an idea. I told him, I say that I give him an overlap coefficient I have in mind, and then actually it's some absolute value and stuff. He told me that. He said that that's very hard to compute. You should give us this. Anyway, before I go there, it's like Okay, we do the multi-overlap in multi-level, multi-covariate X is hard to operate. But we know propensity score is a one-dimensional summary of the multi-dimensional X. So let's just look at, we essentially look at the overlap of the propensity score. That would be good enough, right? So then we just, then we can focus on the overlap in the propensity score distribution. And again, that's a common practice in causal inference. And again, he come up with this coefficient. Again, later, someone told me, oh, what do you use there is something called Bhattacharyya coefficient. Bhattacharyya had done that in 1930s. So everything is reinvented, right? But so what is this Bhattacharyya coefficient? We call it the overlap coefficient. Bhattacharyya coefficient is defined like this. It's a nice thing is below 0 and it's between 0 and 1. And when this equals 0, the support of this two, it's like no overlap whatsoever. And if it's 1, it is overlap almost everywhere. But the beauty of this is computational advantage. And we do all the calculation. I actually wrote this problem in a mass computation problem. I say like, you can prove this. When you have a beta distribution, a propensity score with a beta distribution AB, you can actually prove the Bhattacharyya, the overlap coefficients is closed form. This gives me my second equation. Now I have two closed form equations. You give me R and phi. I can solve A and B. I can solve mu and sigma squared. So you only need to give me two parameters. I can determine the propensity score distribution. There's a lot of approximation go into this, but I think it's relatively reasonable. Okay. Again, this is the part I think is most of the cute part. And then when I do outcome, it's not as nice. So also visualize. I mean, again, this overlap coefficient, of course, is mathematically defined, right? It's a Bhattacharyya coefficient. How can you tell a doctor about Bhattacharyya coefficient? So I actually did some visualization to show that it's actually recently we realized this Bhattacharyya coefficient, even though it's supposed to be between 0 and 1, most of the time, in terms of propensity score, it concentrated actually between 0.8 and 1. So don't think that below 0.5 is bad. Don't think of it as a percentage of overlap. It's really concentrated between 0.8 and 1. So it's like, so you can see like here, when you have a balanced design, you can see the 0.8 is already pretty bad. Like because when you do an observational study, you always tell people like, if you have pretty poor overlap, just stop doing it. I mean, it doesn't help too much, but so you can see. So Bhattacharyya, so I gave a rule of thumb. Like here is kind of rule of thumb. It's usually 0.95 is very good. It's good overlap. 0.9 is already medium, and 0.8 is pretty poor. Okay, so that's I usually tell my medical collaborator. I say that, well, what do you think your overlap would be? They say that it's good. Then I'll give it 0.95. Of course, here there's kind of you would have some leeway or some like imprecision, but this is basically theory-wise. This is the limit I can push. Okay, so yeah.
You got two beta distributions, a red and a green here, but you're
no. This is actually one. This is propensity. Good question. So this is actually propensity score distribution. And I use a propensity score. No, this is the propensity for the treatment group, propensity for the control group.
It is two.
Yeah, the two, but the
marginal is beta, right?
Marginal is beta. Yeah, exactly. But you can actually easily calculate 1 minus e. If your marginal is beta, you can actually have this. I actually don't have. Yeah, you can.
That depends on the conditional distribution.
Yes. Yeah.
You weren't specifying a conditional distribution for A and B.
No. You can say, but I also know R. Also know I also know this guy. So again, if you think of propensity, I can write it down. If you think of propensity score, it's because I'm doing actual Cox extension of this. We just did that. So you think of the propensity score, right? This is a propensity score distribution. And if I have this if I have this E, I would also have the 1 minus E. And then if you just use the definition of conditional probability, you can just reversal it. You can get both. You can get both. I can show you. I can show you that. So it is. Trust me. This one is purely just based on this. It's actually you would get the propensity in the treatment group and the propensity in the control group, just have the marginal distribution. And of course, I also have the marginal distribution of the treatment. That's the key. You need to have the marginal distribution of the treatment, like the treatment proportion. Yeah, I can write it out. Yeah, I know. I wish I have the slide because we just did this like last time, and I can write it out. I just it's almost like qualify in front of you. I'm gonna write it down and I can show you, but I don't want to take 5 minutes because I'm nervous in front of you. So I'm not gonna do it here. But trust me, you can do that.
Conceptually, you have how many A and B to determine? Only one set of A and B, or
Yeah.
two sets?
One set, A and B.
One set A.
Yeah, that's the marginal distribution of the propensity score. Yeah.
So previous slide, so this coefficient is actually the Hindenburg.
Yeah, exactly. Heading
1 minus 5 is the Hindenburg distance.
Heading distance. Yeah. So it's we checked. We first cite Headinger, and then we further look. It's actually in 1930s. Yeah. So exactly. So this actually machine learning people use this a lot.
It's called matrix space.
Yeah, exactly. So but I further dig. I find the first it's come out from the Bhattacharyya. It's called Bhattacharyya coefficient.
1 minus 5.
Yeah, 1 minus is equal. Yeah, that's true. Yes. Okay. So I need to speed up. So we solve for the distribution of the propensity score. So we have give two pre-specified. Again, you give me the treatment proportion and the overlap coefficient, and I can solve for A and B because I have two conditions. Actually, to prove this is also some trick. And this is just forget about this. Basically, we prove that this phi is indeed monotonically increasing K. But the point is that these two actually also give a 1-to-1 map. And the proof of that is actually some math proof. But recently I find there's a simpler proof, but it doesn't matter. The point is that with these two conditions, you actually have you can uniquely identify A and B. And even nicer is, because it's monotonically increasing, this actually, the solve this problem is a bisection, because the monotonically increase, you can do it very fast. So it's very fast, it's computable. Right, so given R and the phi, I can solve for K by second problem. So the logic flow is you can investigate and give me the proportion of treated and the overlap coefficient, and with that I will solve for a beta distribution AB, and then that will give me the logic normal distribution because there's a closed form map, and then give this to I basically have my marginal distribution of propensity score. Then I can just calculate this, both this and that. Okay, so that is all, and this turned out to be very useful for later extension to Cox model, to multiple, multiple time point stuff, because the propensity score is always there when you do trial emulation. Okay, so that's the propensity score part. I think that's the most fun part. And then we get to we still need to define the distribution of the potential outcome. Okay, again, the Lyapunov Central Limit Theorem will say, well, you suggest that we can just approximate the outcome also by potential outcome by x beta, right? It's a normal distribution, but we need the mean and the variance of, and even worse is we need the potential for the potential outcome. The challenge is we might, but we might not, at most know the observed counterpart of this, not the potential outcome, but the observed counterpart. We might know the mean and the variance, but it later turn out we don't even know this. But to construct this problem, I still need to have this. So in observational studies, we know that these two, potential outcome and the observed outcome in the same arm, they're not the same because of confounding. And so particularly YZ is actually correlated, the confactor is correlated with X. So then this make us realize we need to introduce a correlation. We cannot just, so what do I mean? This is size the heart. so okay. So what we try to do is we know we need to solve those, like we need to somehow characterize the potential outcome distribution. Okay. How do we characterize that? And what we currently know is, again, by the previous, we would know the propensity score distribution because, all my previous calculation, right? So then, again, this is all pretty mathematical, this part. In the end, we want to have something interpretable, right? But The mathematical is like the idea, the trick. The idea is like, well, we can project the counterfactuals into the space expanded by the propensity score. Okay, so again, the propensity, I cannot deal with the multidimensional x, but I can deal with x, and so I just do projection. But anyway, the point is that I would need 6 parameters to characterize. So for the y0, I need the mean, the slope, and the variance. And for the other potential outcome, same. It's basically for each potential outcome distribution, I need 3 parameters to characterize that. Same problem. If I have 6 parameters, I need 6 constraints. So how do we define that, right? And that's just getting hard. So we need to use 6 summary statistics quantities to use of the observed y to solve for 6 parameters. So we say that, well, if you do know the observed y, the mean, and the variance, and this is the more difficult part, and I will spend some time talk about. And you need to know the correlation between y and the propensity score. Again, this one is very hard to interpret. Okay, but the point is that we know that if those are the observed ones, somehow if we know that, that's probably make our life easier. So and this is for z is for each arm, treatment arm and control arm. So I do have 6 observed quantities, and I can solve for that. So with input, if I can have the 6, if I do have the observed for each arm, I have the observed, the mean of, I can ask my PI, say, what do you expect that? Well, it turned out that I actually don't need this. But to have the, to solve, think of mathematically, if it's solve the 6 parameters, I need 6 constraints. And this is this would be our input. So then if we have 6 input, we can indeed solve for this distribution, and then we're done. Okay, I know there's the details here is kind of I don't have time to go through, so I quickly just go to further simplification, and then I will go to this slide to tell you what this role is actually. This turned out to be a key thing. So that is 8 input, well, 6 inputs is still a lot. The doctors want as few input as possible. So then let's simplify that. So how do we simplify it? In the design stage, it's probably okay to say the treatment group and control group, the variance are the same. That's reduced to 1. And also say the correlation, the mean you cannot say they are the same because there's no reason to think they're the same. But the correlation, you can also think they're the same. And another thing is, of course, people, when we talk about treatment effect, it's much better to talk about standardized treatment effect because you don't want your scale change and the result change. So then you just require the standardized. So then this kind of S is also like folded into the input, right? Then did all of that, we proved the formula. This looks very complicated. It's, look at it, okay, don't even look at it. So, but what is fun in this is, so this is a formula with all of that input, complicated. But what is interesting is we notice that this formula actually does not depend on mu. This is all the variances. So we actually don't need to know the mean of the observation. That makes total sense because in reality, treatment effect is what we care. So that's what is treatment effect. That's the difference between 2 groups. We actually don't need to know the difference is what we need to. We don't need to know for each arm, treatment group and control group, what the exact the mean is. And the funny thing is, from the math, originally we derive all of this because we need 6 parameters. Or we need to identify 6 parameters. We have, 6 inputs, and this formula we need that. But after you do all of that, you realize this result actually, in terms of the variance, you don't need the mean. That's great. That means that saved my another input. I don't need this because my formula don't even need this. And nice thing is in RCT, this is just reduced to the 2 sample t statistic. Okay, so again, that's further give us a confidence that this is not something made up. Okay, so now the key question is, I still have the task of telling people what is this role? What is this role? Remember the role, the definition is this? What is this? Actually, the paper first under review, and then people ask me, well, what is this? Can you tell me anything about this? I say, well, my original idea was, we don't know any information about that. So make it a sensitivity parameter and then vary it from 0 to 1 and see how it varies. But then we actually realized this also have a nice interpretation. So it's complicated, but just look at this. Again, Z, you can think of this, Z doesn't matter, it's the treatment group and it's the same. So what we have, what we prove is this inequality. Again, it's my student did it. So it's this rho square will be bounded by the R square. So what is R square? R square is basically a hypothetical, the R squared value of an outcome model. Basically how Y, if you fit a distribution of Y given X, how this expanded variable explain your Y. It's the R square of that hypothetical distribution. The nice thing, again, this is bounded, not exact, right? The nice thing is give me an interpretation of this key input, the parameter I need. So essentially, so what is R square? This quantifies the outcome confounder association. Because if my X, it's a correlation basically between Y and X. So, and also in reality, so when R equals 0, or rho equals 0, this is actually RCT. This is reduced to RCT. And the larger R square, also that means larger rho because that's bounded. It is further away from RCT. So you need actually larger sample size. So again, what I think this is like the insight we get from this simple inequality is it tells us actually this is how X predict your Y, and this is precisely the outcome confounder association. And we know that's precisely how that's one of the paths that a confounder affect the confounder can affect both treatment and outcome, and this is characterized that path. And propensity score characterizes the other path. So that practically that makes sense to us. Okay, so then that's just so to kind of get all of this thing together. It turned out that both RCT and observational study require two input parameters, alpha, beta, R, and the standardized sample sizes, effect size. That is just standard. But in order for you to do observational study, you actually don't need too much more. You only need two additional input summary statistic. One is overlap coefficient, which quantify the strength of the confounder treatment association. As with phi goes smaller, sample size will increase. You can prove that. We think that you don't need to prove that. The other is a correlation. Again, correlation, what is this? This is basically quantify, essentially hypothetical. This is a little bit harder to, this quantified strength of a confounder outcome association. Essentially, you can ask your collaborator, say that, what do you think? Well, it's R squared, it's still hard, but at least it has some interpretation, right? What is the R square of a hypothetical, like you think your X can explain Y? But in reality, I actually went to the studies I often do. Most of the time, R squared is actually pretty small. We teach our students like R squared 0.7, 0.8. Most likely, you never had that. So my student went to 2 sigma quant. They told me that, in medicine, we might have sometimes good luck, we have 0.2. But in quant, they have a lot of variables to predict the stock. And the R squared is usually 0.0001. And you say that with that 0.0001 can earn you millions or billions. And so then that's good news for me, because here I know that R squared, I know it's bounded by R squared. So if it's small, then I can just put my rho as 0. Forget about it, right? 0, I don't need to force my collaborator to say, what is your R squared? That is hard. And then so indeed, we actually find that, and this is actually important. The result is pretty sensitive to this rho thing. And and most of the time we find it's actually R squared is pretty small. You can still do a sensitivity analysis, but the range doesn't need to be too high. Okay. So again, I was very happy with the result, because that's precisely like we did all of this. Our conclusion precisely matched my understanding of confounding. What is a confounder? Confounder have two paths. Two paths is one treatment, one on treatment, one on outcome. And this is indeed tell you that that's all you need. Okay, so I think that is, yeah, I hope the doctors find it's easier to use. And just to wrap it up, so I did simulations and we checked the result is actually pretty. So how do we design the analysis? We actually have a kind of real study, RHC study, and then we, of course, the power, and then we use that to generate replicas of the data, and then we know that like we have a nominal power, and we try to achieve. They use this. I mean, it's complicated to explain, but I'm just saying that the result are actually pretty good. There's one condition. That's when you propensity score, you know, IPW, the problem is when you have extreme weights, everything just messed up. So when actually you have extreme weights or your overlap coefficient is low, it's more sensitive. So my idea is always go to use my other work, go to use overlap weights. Or you say you use matching, but again, if you already do matching, or IPW with trimming, why don't you just do a smooth version of that? Overlap weights, and then you can do VIF typos. But that's for another day. But the point is, so this is, I can summarize what we did. So by looking at the variance hierarchy estimator, the variance distribution, variance form, we realize we decompose the problem into 3 components. We need to know the propensity score distribution. We need to know the potential outcome. We need to know the correlation. And for the propensity score, use the Lyapunov that trick. We know that we can approximate by log normal, which we in turn approximate by beta distribution. Give us a lot of nice things to identify that. So we have 2 parameters. Because we have 2 parameters, so we need 2 constraints, and we use treatment proportion and overlap. That's where we decide to use the Bhattacharyya or Hedinger, the reverse of the Hedinger one. And we solve that problem. For the potential outcome distribution, we need 2 parameters. And again, we need a lot of inputs there. Essentially, we need to know the distribution of X in 2 groups, which we again summarize, use our propensity score. The other one is the key is actually the correlation between Y and X, which we quantify by beta by rho, and then this is the same thing. This appears here again. So this is kind of the flow chart how we solve the problem. Why I have this flow chart? It's not really in the paper. Is we did this not now. I'm presenting you the way we figured it out. But when we did it, we actually just first come up with a lot of things without this clear picture. We just, when there's a problem, we find a solution. And then when I tell the story, I figure this is a great way of telling the story. But the original discovery process is actually not this. It's like we actually worked from here. At that time, we didn't even know we would need the correlation and stuff. So but again, you want to, but this turned out to be a good way of summarizing things. And some extensions, I know I don't have too much time. I've finished. So we all know that in medicine, well, this is the most important thing. Anything like this normal distribution, everything's nice, but 90% of work in clinical research is survival. So how do you do survival? Nice thing is, well, and also the doctors just obsessed with Cox model. No matter how you tell them, like you probably want to have care, like the survival, other estimate, they say, I want hazard ratio, okay? And so then you do the weighted Cox model. I mean, again, like when you do trial emulation, you do the weighted marginal Cox model. And then all the maths become different because it's partial likelihood, it's weighted partial likelihood. Same, you still need to do, again, the same idea. You need to approximate this variance estimator, use some quantities. How can you reduce it to just a few quantities? So it took, again, a lot of genius thinking of my student before, 1 month before he went to hedge fund to figure out. So technically, it's much more complex, but again, it's trackable. Our idea, this beta propensity score helped us, but then still other things. So we're basically done with this. I'm now wrapping it up and put it in the package because I know that if you want doctors to use this is a must. And also I did the extension to the repeated outcomes. That's much easier because if you have a continuous outcome, everything's easy. It's just time averaged outcome estimate. but I did that too. It's a weighted regression. And of course, binary here, we just say, you can binary just use a linear probability model and then just treat it, just use a conditional, just use the normal distribution to approximate that. And because again, there's some technical difficulty. So that's, and also we did the ATE and ATO, other estimators, both weighted ATE. So this, again, with continuous outcome is not too hard. With survival, it's hard, but we all know that kind of worthwhile. Before I do this Cox extension, I don't think too many people will use this. After this, I feel much more comfortable. And of course, in Biostat, it's very easy to, I did a lot of simulation. And so in Biostat, it's very easy to, I mean, you guys all understand that to advertise your work, you do a lot of customer service. What is customer service? You need to write your package. Not only you write your package, you need to go to write your tutorial. And not only in stat journals, actually in medical journals. And you go to give a talk, like I'm now giving a talk, but of course I give a talk, I'm gonna give a talk in the medical school, Duke Medical School, actually in next week, and nothing technical going in that talk. I would just tell them, you just need this additional. Oh, I would say that for the survival, actually turned out that you only need actually one additional. Oh, you need a censoring rate, average censoring rate. You also the other one is what I forgot. It is basically you just need an additional. Oh, you need the. Do you need the event rate? I forgot, but it's also it turned out. Oh, you need overlap coefficient and censoring rate. That's all you need. Oh well, censoring rate is not. I mean, even for RCT to log rank, you still need that. So it's also like a very simple solution. And again, so we're now doing all the customer service. So this is a package. Now we're writing the survival into it. And all the papers, this two-man paper. This paper we're wrapping up in a week. This paper is now under review. Hopefully it'll be out soon. And my plan is once both of this out, I will write a tutorial for a medical journal. And hopefully people can use it. Thank you.
Questions?
Yeah.
So, nice talk. The one question I had is, suppose say if I ran as you said, you have a propensity score distribution.
Yeah.
And then if I run a regression model of Y outcome on the dummy variable for the treatment plus beta times the propensity score, and I have a propensity score distribution, and then the beta there determines what my strength of association with the outcome.
So you say you're going to have an outcome model here, like a Y given, so the dummy for the treatment. And you have
I do power calculations under that outcome model.
Yeah.
Do I get a different result, or how?
Oh, as I said, that in causal inference, there are basically two ways of identification. One is weighting, the other is outcome regression. So it depends on why I didn't do outcome regression, because again, there's just so many ways of doing outcome regression. So it's very hard to outcome regression. The thing is, if the model is correct, that's the most efficient thing you can do. But who knows whether your model is correct? So again, when I do sample size calculation, I just need to give a rough guess. So I choose I don't know the answer to your question. So it might be, again, I cannot decide because I don't know what model you're going to use, whether your model is a true model or not. But use propensity score, I know at least it can, I can get some result like this, which give me some theoretical guarantee. Yeah, so we actually have made a conscious decision. We don't go with the estimator. Like, again, I hear the estimator start with is weighting estimator, because that is make the problem mathematically trackable. Outcome model, I don't think so. It would be different, but again, I don't even have a method to do that. Yes.
You say again, how you get an estimator to come up with phi?
Very good point. So the answer, this is, so what I did in those are distributions. So I basically provide a lot of this kind of,
So you actually just show them some.
yeah, just show like what you choose, and I give them some threshold. I say 0.95. Yeah, this is mathematically come up with, right? So I just show that I do think yours are more like this, or more like this, or more like this, and just give me, yeah.
One other quick thing, I mean, it reminds me also that in the survey literature, there's sort of Kish's approximation for sample size adjustment, like 1 plus the coefficient of variation of the weights to inflate.
Yeah. So
If you got this fixed, you could then plug that into there. I mean,
exactly. So that's a VIF, the variance inflation factor.
it's a conservative estimate, right? So it doesn't.
Yeah. So
Yeah.
that's precisely the thing we are actually now also used in the Cox version, especially like that is a VIF, right? So that is basically variance. Basically, that's a design effect of Kish. And the Kish, well, you need to know the weights. But now with this propensity distribution, I actually have a closed form result of that.
Very cool.
Yeah. So yes, we are doing this.
So follow up,
Mhm.
question a little bit back. My head around what I was going to say, which is so. So the IPW is sort of known to be pretty inefficient compared to alcohol.
Yeah.
So you're going to run your thing based on IPW, and you're going to say I need 970 people, right?
Yeah.
You know, at the end, if you'd run a more efficient analysis, maybe you only need 300.
Okay.
So you're giving like an answer which might make it impractical in the end. So you don't your outcome regression in the end.
I actually have an answer to that. It's I thought about that problem. First of all, if you have good overlap, like in randomized trial, I mean, just an extreme case. IPW, overlap weights, regression, the result all more or less the same. The efficiency also gain is very little there. So the efficiency difference really start to show up when you have bad overlap. So indeed, again, my suggestion to people is if your overlap is getting pretty bad, don't do IPW. You actually will you can use overlap. Again, I use overlap weights because I look at your overlap weights most of the time as efficient as a correct regression model. And again, here we indeed have closed form of overlap weights, and I have some simulation to show you. Like if you use, again, you are mimicking observation. So this, do I have overlap? I don't have overlap weights here. The sample size is much smaller. And based on overlap weights, you basically need to change your estimate. Then it's much more efficient. So the thing is, if you have bad overlap, even regression will be still inefficient. Even if you have a correct model, it will be quite inefficient. I mean,
More efficient IPW.
yes, but again, if you use overlap weights, that's more or less as the most efficient outcome model you can have, and the sample size is much smaller. I don't have it here, but I'm looking at that. It's much smaller. So again, it's almost like I'm a car salesman to sell my car of overlap weights, but that's essentially what I say. Yes, when you have bad overlap, don't use IPW. Actually, you go to use like you change your target estimate to become the estimate of the overlap population, and you get much more efficiency out of that. The sample size is much smaller. And I have simulation to back that. And I know, based on my work with overlap weights, it can approximate basically the power of the most efficient regression. Well, it's still a little bit off, but it's almost as good because, again, what it does is it focuses on the overlap population, and you go back to this emulated like clinical trial. And in clinical trial, there's no difference between all these methods because it doesn't matter.
Your formula, your software is going to do calculations assuming you're going to use overlap weights or assuming you're using IPW.
You have a choice. You have a selection there. You have select. I should have it. Yeah, you have a selection. You have a weight. You choose IPW or overlap weights, and it'll give you different things. Yeah.
So I think it's an interesting work. And one thing I'd like to clarify is that we know that the estimation of the coefficients, the propensity score affect their, uncertain qualification of your treatment effect because there's another source of estimation.
Yeah.
So I try to clarify that it is yours, Lyapunov Central Limit Theory, overcome that kind of uncertainty because you're just
No. It's
no. I just seeing that the whole X transpose beta becomes a standard normal, I don't need to really deal with the uncertainty coming from the estimation of beta coefficient differences. Is that the trick you used in your?
Well, no, I didn't use that. So actually, you are.
How did that?
How,
That's my question.
no, I didn't. So I'm actually almost thinking. I didn't even think of estimated propensity score because I just use the fixed propensity score. I ignore that.
Fixed.
Yeah, beta is fixed. Yeah.
If you estimate beta, you.
Yeah, you will have.
Additional.
Yeah, actually a classic result of that is you use estimated propensity score. It's correctly estimated. It's actually reduce the variance. That's only with IPW. That's a classic result, right? But in reality, we're all talking about I look at the efficiency gain is very little. So it's like in reality, when people do this, the big problem is the overlap. The difference of whether you take into account of the uncertainty when you estimate propensity score is so small that probably in real studies, you're gonna lose because of attrition or because of missing data. You're gonna lose that. That is much bigger concern than like the difference in between whether I can use like a sandwich estimator but that's just too complicated. So here I'm just using beta, the fixed one, and use the Lyapunov. I didn't use any trick there.
Probably overthinking about your trick. I thought this.
No.
The way you're.
Oh no. This is just purely give me the kind of the motivation. I realized, oh, this thing people use a single Gaussian distribution. That's a reason. Like they're actually theoretically, it's not like it's actually have some ground there. Yeah.
Thanks to the speaker again.
Yeah, I think
Really traditional style.
Yeah, I have a.
You can classify.
No, it's a what?
Matter is a beta.
Good approximation. Yeah, I included that.
And I was in China, so I feel that I probably stayed.
I would just say that you should use CodeCloud to model your dependence. How about
Single word.
Oh, what about it?
I do. Your question is precisely asked me yesterday, and we have a problem.
It's odd to have a marginal distribution when you're really interested in conditional. Is it given treatment or?
Yeah.
We have what we do is we draw the distribution of propensity score for the fixed.
That's what these are.
Huh?
That's what these are. This is going to be right?
Yeah, exactly.
So it's conditional on the seed, right? No sense.
Like
Again, I.
The slide, it's only marginal, it's not conditional.
It's not marginal.
Junior.
No, it's not marginal.
It's like conditional on Z, right? Somehow you know. Distribution, we don't think about conditional on Z.
But I have one, I have three, I have a R, I have.
It's going to have how you can get over the difference between two distributions, right? When you're specifying the conversion. Yeah, I guess not. This is but it's not on C. So this is a beta. But what you're drawing on the next slide is the combination of those two things is beta, not each of them was a beta.
That's what I mean.
Yeah.
So these are means themselves, right? It's the average representatives of average, the average of colors.
It's just not, yeah.
Okay, and you don't mind that, right? 我来了就帮我放在这里，放在这里。我自行车，我今天自行车到这里来，我这晚上最后一圈。挺远的呀。
So in the end, we will say, oh, because it's in the
我有
design
条件
stage,
的，
we don't know because
但是我的是我，回家拿车就可以到那里。
the design stage, you don't know. Yeah, that's
会你会把不用把这个。你住在哪里？我开车住在哪里？你就帮我装到这里。
it's
哎，那
already
个
like.
所以只要
that's
我
the
还
point.
蛮近的。
Oh, 王老师 that's the reason. I
Oh, I see.
对，那哪来的片？
Nothing but.
那你
是开软式。
Yeah, I'm very excited. Yeah, I'm very excited because the student is really just. It's a very crazy one. Yeah, I make assumption because I had that's the only thing I said.
streamline analysis, you start using
要不问一下 Peter，
learn over time.
我们现在有一个人先去就行了。
Actually, both are.
我稍微踩你一点。
Yeah, it's that's because originally we didn't do this step. I just have what E and S and reviewer say it's too hard to come up with. Then we started to realize, and then you actually can interpret.
Yeah.
So it's yeah, we have been.
For many years, like I see the Bhattacharyya before it's like, the
Oh, yeah, I
like modeling the Slinsky, the Russian.
Yeah, so my student
Like
like
see those there.
my original idea is to
Yeah.
have a like the another version is absolute value, but then that is not smooth. So then it's a discrete. Then my students say then you cannot do this kind of
No, this is
This
a
kind
very non-parametric talk.
yes,
And
very
the
non-
question they
yeah, it's very
ask is,
non-parametric. Yeah.
if you put in more assumption, of course, you have distributional,
And
then
then-
the variation will become
Then it becomes
smaller.
like yeah,
Right,
because
but for power calculation.
you
this
want the
will
minimum assumption.
give- Yeah, this will give a bound.
Yeah, this is
And
a
then-
very
Right,
non-parametric.
very non-parametric.
Yeah, I think again the trick of this X beta was really the starting point, and like we just say yeah, how do we generate like
And you don't actually need to use it. You just really basically justify.
justify?
beta
I just
to do
justify.
the
Yes.
estimation,
Yeah.
right? So it's just justify how you,
Yeah.
to satisfy the reviewer.
Yeah,
But
yeah.
it looks so much nicer with justification.
Yeah, it's very
Rather
nice.
than I just.
So I think
say
usually with
beta.
stress, you don't have the. I just like it so clean.
Yeah, it
Conclusion is very
is.
clean.
And
And it's
the
easy.
kids probably earn a lot of money.
He's the best student I ever had. Yeah, he's in quant and now earning all. But we still finish the course. But really, the course is far more difficult. The cost of the calculation is much more.
Right.
But we again also.
But people actually now are funding using this observation.
Every day, like also it's because I asked, like in Picori, every study they need because again, people think observational study often they think this large scale, but it turned out that now particularly for rare disease, it's very hard to come up with all the samples. So actually they use this quite a lot. I fancy that she has some collaborator asked precisely this question.
Yeah, exactly.
The months I started to work on this, people's like I got 3 inquests about this, and I really okay. I know this is some work worth doing.
No, it's beautifully done. Yeah. So
Oh, thank
the way you can approach, but in terms of those you don't have close form, but you have this beautiful framework, you could actually
Yeah, so that,
inject the synthetic component to.
yes,
as long
exactly.
as it's in
Yeah, I think
in
like
the
the propensity
package
score
that-
give us a lot of
Yes.
leverage for the
Yes,
observational study.
Yeah.
The outcome model, yeah, is far more complex there. We can do different things, but again, as I think as Michael just said that you can do this variance inflation factor. Before you need to know the distribution of weights, but now with propensity score distribution, you know that you can approximate a beta distribution, then that's also done.
And then also less parameter to control.
Yeah, exactly. That's a
Those
close
you
form.
have to
Yeah.
know a lot.
Yeah,
right?
so
For even for doing sensitivity
Yeah.
analysis, it's much more convenient.
yeah.
Really nicely done.
Well,
I
thank you,
enjoy
thank
your
you.
talk.
Very
Very
well.
well.
I think this is my best work in 10 years. So the first best work is the one I keep saying the overlap with overlap.
No,
I think-
actually, you just want to have couple of couple
Yeah,
of
I
work
think- but I
that
think
have a
that's
longer impact, right?
Yeah, I think
This
this,
I think would stay.
will stay, I think, yeah, and especially after we done the COPS.
work.
Yeah, it's probably will get published in annals. We do the Cox version. I mean, if you want a medical doctor use it, have to be Cox, and that also I have very good solution.
Right, right.
And then package.
Yeah, well, keep the package going.
Yeah,
Because,
we're
you know,
package
some
is
like
similar.
Yeah, like NGC, CVE, like by Simon Wood, the reason later on, all the reviewer being very polite to them is they are grateful for their contribution
I
of
see.
having long-standing package and keep it
Yeah.
Available.
And this is actually pretty simple, our package, right? Because it's just some formulas. Like there's not
Close
much,
form.
yeah, it's closed form.
I think you can extend it so much more because you have the framework, even you don't have a closed form. You know,
Yeah.
you could easily inject.
Yeah, then
like,
people ask me
like
about the
exact
multiple
text.
treatment. That's indeed what I did, but I need to see that how long the interest I have. Yeah, but I will write again paper hopefully in the tutorial. We know the BMJ education editor.
Okay, yeah.
So if we can get in the top medical journal, then it's
that would
really
be,
big.
that would really help.
Yeah, so it's yeah, 售后服务.
Yeah. Okay.
Are you going to Taiwan? Are you going to Taiwan for the conference in December?
Yeah, I'm going, but not for the conference. The
Okay.
reason is before when I was invited, and both my parents just passed away.
Oh, sorry.
So, but before they pass away, the health problem, every time I go back, right, and then I need to spend time to,
I see.
you know,
I
take
see.
care of them. We have higher help, but I have a younger sister stay there.
Mm.
She keep firing people we hire. So, you know, I was doing the long-term manage.
I think we will have similar issue like in
So,
10 years.
yeah, so it's again, I really, you know, hire good people is really the way to go, and then you go back like every maybe couple of months.
Mhm.
And yeah, so I turned down so many
I see.
invitation.
This will be my
including
first time to
some
Taiwan, so I'm really looking
I
forward to
will
it.
be there. So actually, G will be there, so I'm going to organize a dinner. And then
Oh,
I'm going,
Juji is, Juji is
yeah,
there, okay.
G will be there.
Okay.
And I think
I'm a good friend with Juji.
Ira. So if people are there, let me know.
Peter is there.
Peter will
yeah,
be
Peter
there?
will be there.
Okay, okay. So I need to ask around. So I have couple places I can take people to
Amazing.
have,
Cool.
yeah.
Yeah, I
One
will
with
hang out with-
Jason Wong, I mean, there's more restaurant discovered by him, so we can try to see, can we be, yeah, so we'll see.
Yeah, I think.
Okay, so I'll add you to the.
Oh,
list.
great. Thank you.
Peter will be there, G and
Yeah.
Ira, and then, yeah, so.
Yeah, I was invited by Jenny. Yeah.
So that means Jenny and Hans will be
Yeah,
there?
they'll be there. Yeah, Jenny actually organized the several sessions.
Yeah.
Nice to
Thanks.
meet you.
Nice to meet you. So then I'll see you in Taiwan then.
see you
Not
there.
earlier. Bye.
Okay. Hi.
I just wanted to say hi, so I'm originally from Duke, I've just completed my.
Oh.
Course of reading some math and science there. I worked with Professor Ryder.
Oh, yeah, I was on sabbatical last year, so you probably didn't see me.
Yeah, no, I was gonna take your causal class. but-
Yeah, no, I was in China,
But-
unfortunately, yeah.
Yeah, but now I'm first year.
Oh, great. So how do you like it here?
It's good, it's less basic. I was expecting some of this to be basic. but-
No, I'm not basic.
Yeah, well, I mean.
I find this kind of stuff much more fun.
Someone, sorry, yeah, you used to do some basic causal.
Yeah, but I mean, I rolled to get tenure. And I realized how they use it, so I stopped doing that.
Josh told me that you said that. You work with Josh, right?
Josh, yeah,
So.
yeah, people don't use that. I mean, like, I think they're brainwash all the kids as if the word basic, but that's not.
I mean, Duke's done better.
Yeah, yes.
I did take the.
This is a great department.
No, yeah, it's biostats and stats work very well.
Yeah, I know,
Very-
yeah.
it's
I
very
have a
good.
lot of friends, I have a lot of friends here.
Cool, yeah.
Oh, nice, yeah, so I will talk to Josh, yeah, Josh, every week I gave him a quiz on Blackboard
Yeah.
about some, like some color inference problem, because he's doing a brilliant.
Really, yeah. He told me he's following like all of Undane's book, so.
Yeah, exactly.
So,
Okay.
all right, nice to meet you.
So I think I just bought a home.
It's in my
community.
你们离这儿有多远？
离这可以
分钟是
基本上就在城的边上了。
你结婚了吗？
结婚了。
结婚了，那你老婆干嘛？
我老婆计算机系，现在这儿有计算机系。
是巴克利还是
faculty
？IC，那挺好的，
对
那是 work out 的。对。
我靠，这边能帮忙解决。
对，因为就是统计系嘛，特别想找那个就是王冠阳。然后他老婆那个就死活也解决不了，然后他老婆也是法国里，然后他老婆还想进 CS 系，但是他做的那个又不太，就是反正 CS 也没给解决，但我也没给解决，最后就没来。对他们就是 work hard 了2年，想给他就是 offer，因为是统计不是又喝了2年西北风嘛，就是2年都没招到人，然后他们就，然后所以就会出现 Richard 锅这种回炉的情况。
哦，是因为这样。
对 Richard 特别搞笑，就是回炉嘛，就之前他后来去了一个大又不爽，然后问这边说还要不要，然后这边正好一个人
说过去，
对，这边正好就一个人没招了，然后就说要，就来了。
就他们去给了一个也是做 Bayesian 的人的 offer，但那个人好像跑到别的地方去，是不是去加拿大了？
不知道，反正去年我在中国，所以那个market 上我也不太清楚。对，你现在你的 collaborator 的问题，你就可以用这个解决了。
对，太好了。
我觉得是挺好的。对。
而且实际上他们好多这种问题，就是它不是说光有 rare disease，而是说哪怕是一个非常 commonly seen disease，但是大家想要看一个比较少的 event 的话，
对，他就是因为像 Picori 经常这种问题经常出现，而且他们现在做 external control，
对，
这个 framework 也可以用，因为 external control 嘛，你用 propensity score weighting 问吧，或者 matching 是一样的嘛，你有那个 single arm trial， 然后你要做一个 observation， 不就变成了一个 observational study， 都是一样的。
是的。
哎，我其实想问一下，这个比如说我可能 miss 了，就是它最后和这2个 parameter 这个 phi 和那个 rho 是单调的吗？还是？
是单调，我们没有证明，但是 phi 肯定是单调的，然后 rho 也是单调的。
对，这样
我最后没有证明，但是应该是单调的。
对，那还挺好，就是到时候会给一个 range， 大家就知道它长度是什么样，就是对。
其实 rho 是比较难，因为 R square 的东西还是蛮难讲的，但是我们后来发现，其实 R square 一般都很小，所以你就做一个 scientific analysis 那个0到1，像我最后不是画了一个。就是你就给，因为他们的医生不就是要 power calculation 要那图嘛？
对，
他们都是要看那个图，就是这个嘛。你看，我们就最后就说你要不停的，就是给了是在 R 这种看不同 overlap， 其实你会发现 overlap 很严重，就是说这个你看它的 overlap 不好的时候，它的需要的就大很多。
它的 decay 非常
它就非常明显，这个其实在这么差的情况下，你就不应该用这个。就不应该用这个，你其实就应该用 overlap weights。当然，就很多人都是 resist 用 overlap weights，我觉得你们都用 propensity score weighting，做 trimming 或者是 matching， 为啥不直接一路到头 overlap weights？ 但是 anyway， 你看像 Jeremy 他们就死活抱着 IBW， 然后说我 outcome model， 那你 outcome model 都没法做 outcome model 就是因为很片面文化，你就不可能做出来这样的题。对，
有这种传统的观念在里面。
对。
就关于那个 phi 和那个看起来那个 overlap， 就是假如说 R 是已知的情况下，是会有一个 phi 和这个 proportions of overlap 的一个 one-to-one mapping 吗？
有，我最近刚做了一下，就说因为我后来发现我们其实 要实际要用这个，还是要给大家一个就是
更直观的一个。
对我画了图，而且我看了一下 A 和 B 的这个，其实后来你就发现 A、B 这个证明，当 A、B 小于2的时候，就是 beta distribution 很奇怪的 beta distribution 那个它因为只要是大于0嘛，但是如果是低于1的话，它就变成了一个 U-shaped，
对，
那就不行了嘛。然后其实就是大于1其实都很差的，就是我们画了一个 A、B 的大于1的那个差别，然后就发现要 A、B 要大于2才比较 OK， 它其实 A、B 越来越大，A、B 越来越大的话，它其实就是越接近RCT。对，然后我这就对，而且你后来发现那个 overlap 就是如果 coefficient 在比如说在0.8的时候，就发现其实 AB 就是 AB 就已经就是经常，然后因为我们做的那个 simulation 就那个 variance inflation，你就发现如果是在2左右，它的就相对应在2的话，两个都是2的话，好像 phi 大概是0.8的样子，还是因为我忘了，它就已经非常 rugged，就是 uncertainty 非常大。然后那个，而且这个不是我们 approximation 的问题，这个是 IPW 本身的问题，就是 IPW 那 overlap 不好。你看像这种情况，如果这种情况，其实 overlap 其实很差的已经。因为就可能因为你相当于大部分的那个 high concentrated 这个 extreme weights right，那它肯定就不行。就是这种，就说大家还能忍，就这个其实就很差了。这个就是应该换 estimate 的，就换 estimate 就是换 weighting strategy 了。所以我现在还在想怎么写，就是告诉我，因为我们在 survival 那篇文章就很明确的，因为那个 variation 更大就是对，就是用 weighted cox 就更大。weighted cox 真是计算特别难，但是刘博我觉得他特别 genius，就是他真的有那些天马行空的 approximation 就能想出来，有很强的数学，然后又有很好的直觉。当你就是像那些一般多出来那个像那个数学上就很 ugly 的表示，然后他一般都可以把它证明出来，比如说用大 O 小 O 就给它就给它放得掉，然后最后这 simulation 结果也是都是就是 match 它的 intuition。这个就很酷。
一确实这么好，其实适合去做 quant。
而且我是说你赚很多钱，然后你回来 support 大家哈。
大家方便。
这个 work 其实真的就真的就跟升级打怪一样，就是因为我们一开始最简单的，比如说你做 simulation， 然后那个 postdoc 就开始做 simulation， 做着做着就发现，哎，我换一个 parameter 差好多，我到底要啥？然后我就说，你可能需要 overlap coefficient， 这完全是我的直觉。然后我就说啊，你看用这个 overlap coefficient， 然后他后来他就发现有各种各样的问题，然后刘博就是 take over， 他就说，哎，这个你为什么 simulate？ 因为 simulate 那么多 x， 你上哪去 simulate？ 他就说，哎，那我就研究 x beta， 就发现哎是 normal distribution， 马上问题就简单了。然后 normal， 然后下面说，哎呀 normal 太难搞了，那搞 beta。然后就是这个也怎么想出来的？我觉得也是很神奇。然后贝塔发现哎很好，而且贝塔还有个这么漂亮的结果。其实这个 work 很盲牌儿就是整个这个就是你看有这么一个漂亮的结果。这个我还在说农数学竞赛，我做那个评委，我还写了这个题。我说你证明 propensity， 然后就是如果 propensity 长得那样，你怎么就是你可以证明这个其实是分析的问题，就是因为 beta distribution， 因为 gamma distribution 有很多那个分析的 trick 可以证明出来。然后而且后来发现这东西还是 one to one， 还是 monotone， 所以用解法解起来又很好解，就是因为它 monotone 嘛，那你就可以用 bisection 会算得非常快。因为我之前想的那个 overlap coefficient， 它是算就是没有 closed form 就很难算，没有 closed form 就非常难算，那你每次你还得数值运算那个东西。对，这个挺 non-parametric 的，就是一个我自己是觉得它就是太 creative， 所以我就觉得这个工作其实是我真的是觉得比加塔大部分的文章都好，但是就是被加塔去了呀。然后后来完了去，现在我觉得 Anos 应该没有问题。
那更好啊。对。
我不 care， 其实我不 care， 但是 Bhattacharyya 直接就说 narrow scope 就给去了。我心里想，你们知道这什么叫 scope， 什么叫 impact？ 就是懂的人就知道这个意思。对。然后，因为现在 Anos 应该在丁鹏手上，他肯定能。那为什么？
那我们直接上去吧。对，就上去开一下，然后我们让郑科把车，他说他要开车过来接我们。对。
来开着他那个 fancy 的宝马。
对。
哎，郑科总是很潮。